Okay, so this is what we did in class. We found the power series to represent 1 over 1 minus x centered at 0. All right, we found that series to be a geometric series with the first term of 1 and the ratio of x. So let's put that to use. All right, find a power series centered at 0 for the function 4 divided by x plus 2. All right, so this is what we know. We know if we have a geometric series in this form, okay, with a is equal to 1 and r is equal to x, that's the series that we can use. So we're going to attempt to fit this 4 over x plus 1 into the form that we already have the series for. All right, so first thing I'm going to do, I'm just going to rearrange the denominator, 2 plus x. All right, at every step, I'm going to maintain what the original function was defined as. The next thing I'm going to do, adding x is equivalent to subtracting negative x. Okay, I know I need that minus in there in order to be able to represent it with a geometric power series. All right, next thing I'm going to do, from the denominator, I'm going to factor out a 2. Okay, 2 divided by 2 is 1. Negative x divided by 2 is exactly that. Okay, so again, at every step, if I were to work backwards, I would be back at my original function f of x. Okay, 4 divided by 2 is 2. Now, I have the function, and I can model it using a geometric power series. Okay, so I have it in the form, I know what my first term is, I know what my ratio is. So this sum is a times r to the n from 0 to infinity. So plugging in the information that I have for the series here, the power series for this would be the series from 0 to infinity. First term is 2. Ratio is negative x over 2, so that gets raised to the n. And because it's geometric, I know that this converges when the absolute value of the ratio is less than 1. So solving for the interval of convergence, again, because it's geometric, it will not converge at the endpoints. So what we did, what we showed, that 1 over 1 minus x, that's a very useful theorem for us to be able to find other geometric representations. Okay, let's look at another one. Find a power series representation for 1 over 1 minus x centered at negative 1. Okay, so we already have the series for 1 over 1 minus x. 1 plus x squared. But these are centered at 0. Okay, and from the power series, we know if we have a center that's not 0, then this is what the power series would look like. Okay, so how's that going to change from what we are, from this series that we've already developed? Okay, so if the center is at 1, then that has to be represented here. Okay, this series is centered at 0. So if I center it at 1, I know that that's x minus the center. All right, so like I said in the previous slide, at every single step, I have to make sure I get back to my original function. So if we think about distributing this negative, that would simplify to 1 over negative x. That's not what my original function is defined as. So what can I do? Well, let's look at, I actually introduced a negative 1 by putting the center in there. So if I want to keep that balance, let me maintain balance by adding 1 there. If I think about this plus 1, if I look back at distributing, okay, these cancel, and now this representation does give me my original function. So we're just reorganizing it to be in a form that's useful for the series that we already have. So this would be 1 over 2 minus the quantity of x plus 1. Okay, again, a quick check. This gives me 1 minus x when I combine my like terms, so I still have my original function. My original function is that 1 over 1 minus x. Okay, now I have to get it into a over 1 minus r. So I need this first term to be a 1. Let me factor that 2 out. So I get 1 minus x plus 1 divided by 2. And then my last step, dividing by 2, that would make my first term 1/2. Okay, so now I've represented it as a geometric sum. So the power series for this function, first term is 1/2, ratio is x plus 1 over 2, so that gets raised to the n power. Now for the interval of convergence, I know that the geometric series converges when the absolute value of the ratio is less than 1. Okay, so this verifies that my center is at -1. Subtracting 1 from both terms, and because it's geometric, oh, hold on. This is a 2, which makes this a 1, and this a 1. Because it's geometric, the series will not converge at the endpoints. Okay, find a power series for 1 over x centered at 1. Okay, so if it's centered at 1, then I need to make sure that I put that in there. Okay, next thing that I'm going to do, I'm going to rearrange this, and I'm going to rearrange it to be -1 plus x. Okay, I'm getting there. I need a over 1 minus r. Secondly, I'm going to factor out a negative. If I factor out a negative, that would give me 1 minus x in here, okay? Because I know that I need to subtract this value of r, so I'm thinking that you should be seeing that, all right, that's going to become our ratio. Okay, let me backtrack a second here. So I put in the x minus 1 because it's centered at 1. So I know that in the power series, that's what the center is going to look like. And so I should have done right from here. If I'm going to subtract 1 to represent the center, I need to add 1 to maintain balance. Okay? So if I cancel the -1 plus 1, all right, I'm definitely back at my original function. That's always the ultimate goal. Okay, so now we have to get it in the form of this a over 1 minus the ratio. Okay, so my ratio, I have to make sure that I have x minus the center in that term. That's what my ratio is going to look like. All right, so I keep this plus 1, okay, because that's what I needed for balance. Now from here, if I factor a negative out of these two terms, the -1 plus x, there's my negative, it'll make it +1 minus x. Now when I put my 1 in here, which was originally introduced to keep balance, now I have it in the form 1 minus the quantity 1 minus x. So now from here, a is equal to 1. My ratio is equal to 1 minus x. Seeing all sorts of things in this problem. If you go back and look through that lengthy definition of what a power series was defined as, it was our coefficient times x minus the center to the n power. So what do I need to do to my ratio? I need to, yet again, factor out a negative so that I can fit it in that form x minus c. Okay, so from here I can automatically see that my center is at 1. So now, fitting it in to what we know the sum of a geometric series looks like. 0 to infinity. First term is 1. So then I have negative x minus 1 to the n. And then furthermore, I can make this an alternating series. -1 to the n times x minus 1 to the n. It's geometric. It's going to converge when the absolute value of r is less than 1. -1 is less than x minus 1, which is less than 1. Adding 1, -0 is less than x, which is less than 2. So the series will not converge at its endpoints. So here's my power series and my interval of convergence. So this geometric does a lot. It eliminates the need for finding the derivatives and plugging them in and dividing by n factorial. All right, let's try. Let me introduce this next one here. Find a power series for natural log of x centered at 1. Okay. Now this method is not, I don't think would come naturally. Okay, so that's why we have to talk about the usefulness of integrating and deriving series. Okay, so these are a couple things that I do know. I know that if I take the derivative of the natural log function, it's 1 over x. This should look familiar. That's the example we just did. I also know for the function 1 over x centered at 1, that power series is 0 to infinity, -1 to the n, times x minus 1 to the n. Okay, so how can I put these things together? If I want to find a series for natural log of x, let me then use the antiderivative of the series we found for 1 over x. So this is what we worked on in class. What would this tell me? Then I can get a series for the natural log of x by integrating the series that we found for 1 over x. Okay, in the interest of time, I'll stop here and we'll look at a couple more examples in class.